The chronology of events that unfolded during the first half of the 20th century brought unparalleled achievements in our understanding of the mechanics of flight. From the basic structures of airframes and airfoils, to the application of thermodynamics and mechanical power, we have seen that the art and science of aeronautics move forward at an exceptional pace. If we look back at the origins of these accomplishments, we learn these were often won at great cost, but also great reward. Our engineering history should be celebrated for its steadfast record of successes and failures that have advanced us to the current state of the art. In Part 1, we will examine the state of aero engine technology at the end of the First World War. Then we'll follow the developments that marked the next decades into what became known as the Golden Age of aviation. At the conclusion of the First World War, the status quo of aircraft engine design is well represented with a few examples chosen. Two styles had emerged prevalent: the rotary air-cooled engine and the inline type liquid-cooled engine. Something that may have been a bit ahead of its time, the engine market was truly global, as these engines were sold and licensed to aeronautical manufacturers worldwide. Better power plant designs found themselves under licensed manufacture in many countries. Moreover, they became the engineering basis for many manufacturers' new aeronautical innovations. From the rotary engine side, the Gnome Aeron 9C was a well-developed example of this type of engine. It succeeded the earlier monosoupape single-valve Gnome variants that featured a novel induction path through a series of intake ports in the lower cylinder wall. The 9C adopted a more modern induction method, featuring tubes directing the mixture to a cylinder head mounted valve with a single pushrod activated valve train apparatus. One of the telltale signs of the Gnome engine was the highly visible copper induction tubes emanating from the case between the cylinders. Of the three main rotary engines, the Gnome powered the greatest variety of airplanes in service during the Great War. The term rotary implies a characteristic that also differentiates these engines. The crankshaft is fixed to the airframe, and the propeller is fixed to the crankcase. In this method, the case and cylinders rotate with the propeller. The Gnome 9C was nominally rated at 92 horsepower at 1300 RPM. Its cylinder bore was 105 millimeters and stroke 140 millimeters, and displacement 10.89 liters, with compression ratio 4.5 to 1. Another conspicuous characteristic of the rotary was its lubrication method. Castor oil was injected through the hollow crankshaft to mix with the fuel-air mixture. The centrifugal force of the rotary carried the oil outward into the combustion chamber, and from there it ejected with exhaust and could not be recirculated. The resulting spew unavoidably coated the airplane and its pilot with a distinctive aromatic mist. Next, the Clerget 9B was a competing French rotary design featuring a standard intake and exhaust valve arrangement with two separate push rods and a simplified connecting rod design. It employed a unique brass piston ring below the wrist pin to contain the heat of combustion from the cylinder volume below the piston. These rings were subject to frequent replacement, and most notable was that the engine could be throttled to reduced RPM rather than intermittently switching the ignition off and on again. More powerful, the Clerget made 130 horsepower at 1250 RPM. The Bentley BR2 was the largest and most powerful rotary to see wartime service, producing 230 horsepower at 1300 RPM. developed by W.O. Bentley from his earlier work with Clerget engines that were built under license by Gwins Limited. It differed materially using machined aluminum cylinders with pressed-in steel sleeves. Lighter weight and reduced rotating mass contributed to higher performance. The Sopwith Snipe is widely considered the zenith of rotary-powered World War I fighter designs. The Daimler 3 Series inline liquid-cooled six-cylinder engines were known to be robust and reliable, requiring less routine maintenance, though their rotary counterparts were also considered lightweight and powerful. As they grew in size and output, the increasing rotational mass of the rotary became a detriment to the aircraft they powered. The linear thrust of the inline engine, however, promised more potential. Less experienced pilots were able to manage the airplane more easily and employ them in combat more favorably. Probably the most effective single-seat fighter of World War I was the Fokker-designed D-7. The D-7 was powered by all variants of the Daimler D3 series engine until more advanced similar designs were introduced. First introduced in 1917, the Fokker D7's Mercedes D3A was rated at 180 horsepower. A final D3 AVU high-altitude variant with higher compression domed aluminum pistons, a modified anti-icing induction path, and altitude compensating carburation delivered up to 217 horsepower at 1600 RPM. An advanced competitor, the BMW 3A inline six-cylinder engine, was the first product for the Bavarian Motorworks Company. Rapp Motorenwerk supplied a proposal to build the engine in May 1917 and had it running on the test stand by September. A few months later, the company was registered as Bayerische Motorenwerk GmbH. Similar in design to the Mercedes D3, it featured a few important differences. It was designed from the outset with a higher compression ratio of 6.4 to 1 and a higher displacement of 19.06 liters. Furthermore, designer Max Fritz employed a novel butterfly valve in the twin-barrel carburetor to effectively adjust the fuel-air ratio up to altitudes of 2,000 meters. This was all accomplished using a special higher-octane gasoline-benzol mixture. Using full throttle at altitudes below 2,000 meters could result in detonation and damage to the engine. At low altitudes, full throttle could produce up to 240 horsepower for short periods. Fokker-built D7s with the new BMW engine were designated D7F in tribute to designer Max Fritz's accomplishments. The Hispano-Suiza 8 series was introduced in 1914, becoming the most widely used liquid-cooled engine by Allied countries in the First World War. The Barcelona-based company's HS8 series was eventually licensed-produced in 21 factories across France, Britain, and the United States. The 8-cylinder 90-degree V-type engine was rated at 140 horsepower at 1900 RPM with a displacement of 11.76 liters and was introduced with the SPAD 7 series fighter. The crankshaft was machined from a solid steel billet, and the cylinder blocks were of a cast aluminum monoblock type. The Royal Aircraft Factory SE-5A was a late development of their earlier SE-5 series and featured a geared 200 horsepower Hispano-Suiza 8B, often turning a large clockwise rotation four-blade propeller. An expansion tank for the cooling system was integrated into the leading edge of the upper wing center section. One of its greatest advantages over other types was its superior performance at altitude. Unlike many of its peers, which were highly agile but also unforgiving, the SE-5A was comparatively stable and easy to fly. Its inherent stability enabled pilots to fire upon their adversaries from a greater distance with higher accuracy. It had a noticeably lower accident rate than comparable aircraft and was known for its ability to be trimmed to a hands-off condition. One of the latest and most powerful engines of the period, the Liberty L-12, was America's attempt to supply aeronautical technology during the war. More of a demonstration of political will than engineering prowess, Hall-Scott Motor Company's Elbert Hall and Packard Motor Cars' Jesse Vincent's collaborative design still raised the bar for a more powerful airplane engine. Its 1,650 cubic inches made 450 horsepower at 2,000 RPM, weighing 845 pounds. Single intake and exhaust valves, a 45-degree V, and simple bronze main bearings became some of the standards of engine technology for the day. From this late war effort, engine design in the U.S. during the 1920s enjoyed a particularly robust investment, netting some of the most important technology gains that set the stage for the rapid developments in the decades to follow. Moving into the 1920s, Curtiss Aeroplane's design work for their new D-12 engine was completed in 1921, amid a flurry of designs for the Schneider Cup Trophy race. The 12-cylinder, 60-degree V upped the ante for liquid-cooled engines to 443 horsepower at 2,200 RPM with 1,145 cubic inches, weighing 693 pounds. Two Curtiss CR3 racers placed first and second in the 1923 Schneider Cup race, powered by the D-12 at a winning speed of 177 miles per hour. Curtiss V-12s prompted a worldwide interest in high-power, low frontal drag design that persisted throughout the Golden Age. In 1924, Curtiss V-1400 was a bored-out development of their D-12, featuring a 5.51-to-1 compression ratio, new open-ended cylinder liner design, and reduced frontal area. Magnetos were relocated between the cylinder banks, and it also featured an improved cam gear design. This 665 horsepower engine powered Jimmy Doolittle's 1925 victory in Schneider competition at a speed of 232 miles per hour. Curtiss followed up this design with their V-1570 Conqueror series, powering many of the Curtiss Hawk fighters of the late 1920s and inspiring V-12 design worldwide. A renaissance in air-cooled engines followed with Charles Lawrence's J-1 9-cylinder radial engine design. The term radial now replaced rotary as the standard for new aero engines, and the J-series ultimately refined to the J-5. The J-5 demonstrated unprecedented endurance and reliability on Charles Lindbergh's 1927 transatlantic flight. Lawrence's company was bought by Wright Aeronautical in May 1923 as the Navy maneuvered in politics to secure a supply of high-power, reliable air-cooled engines to replace their liquid-cooled Hispanos. Lawrence engines subsequently became known as Wright Whirlwinds. The Wright J-5 Whirlwind made 220 horsepower at 2,000 RPM, weighing 500 pounds. Features of the J-5 that set the standard for high-powered, lightweight aero engines were improved steel cylinders with machined cooling fins, sodium-cooled exhaust valves, hemispherical combustion chambers for better breathing and cooling, completely enclosed rocker arms and push rods, and dual ignition systems. The Wright J6 followed in 1928, setting even more standards. It featured a supercharger with a 10.15 to 1 impeller gear ratio and delivered 300 horsepower, later increasing to 450 horsepower with a 6.3 to 1 compression ratio. Designers investigated improved streamlining with the faired nose of the exhaust collector, which became typical of early 1930s design. In 1924, Pratt & Whitney Aircraft Company was formed by the fortuitous departure of Frederick Rentschler and George Meade from the Wright Aeronautical Corporation. Their first design at the new company raised the bar yet again with the 9-cylinder supercharged R1340 in late 1925. The R1340 initially developed 450 horsepower and later up to 750 horsepower at 2200 RPM, weighing just over 800 pounds. The name Wasp was applied, beginning a long-running family of radial engine products. The Pratt & Whitney Wasp powered the Boeing F-4B and P-12 series, the GB R-1 Super Sportster, and the Boeing P-26 Peashooter. Pratt & Whitney followed this design in 1929 with the equally successful R985 Wasp Jr. A smaller version of the 1340, it developed from 300 horsepower to an eventual 450 horsepower at 2300 RPM. The Granville Brothers GB Model Z Super Sportster was built in July of 1931 to compete in the annual Thompson Trophy race. It attained a speed of 267 miles per hour in the Shell Speed Dash event and won the Thompson Trophy race piloted by Lowell Bales at a speed of 236 miles per hour. Other successful designs capitalizing on this compact radial include the Beech Model 17 Staggerwing, the Spartan Executive, Lockheed's Model 10 Electra, and Model 12 Electra Jr., and the Beechcraft D-18 Twin Beech, contributing greatly to the future of high-speed and business travel. During the 1920s, Italian aeronautics gained momentum with the Schneider Cup trophy competitions, and in 1925, Aeronautica Machi engineer Mario Castoldi designed their M39 seaplane racer for the 1926 competition. Powered by an 850 horsepower Fiat AS2 V12 engine, the Italian team won the 1926 race at a speed of 246 miles per hour. For the 1929 race, Castoldi designed a new racer, the M67, to be powered by a much larger W18 Isoto Franchitti ASO 1000 engine. The new engine was rated at 1,798 horsepower, driving a 3-bladed propeller. Many innovations were incorporated to offset the tremendous torque of the massive engines, but a series of mishaps prevented the team from completing the race with either of the M67s entered. Fiat had attempted to ready a 1,050 horsepower V12, the AS5, for the 1929 competition, but was unsuccessful in the limited time available. They did, however, pursue a follow-on to that engineering investment to build what became the most famous of all Schneider Trophy race engines. The AS6 was conceived for the Machi Castoldi MC72 racer. The concept of coupling two AS5 engines was an expedient to achieve the required horsepower with a minimum frontal exposure. The engine was boosted to 1.82 bar, or 53 inches mercury, and drove contra-rotating propellers, greatly improving its water handling for takeoff. Each of the connected engines drove its own propeller through concentric shafts in what was essentially a twin-engine, centerline thrust arrangement. The AS6 3066 cubic inches, 3100 horsepower, at 3,300 RPM powered the plane to an unprecedented and yet unsurpassed 440.6 mile per hour seaplane world speed record in 1934. Fiat pursued further V12s of more pedestrian performance but excellent reliability for the military in the 1930s. The Fiat A24R of 1931 was built in geared and direct drive, displacing 1,972 cubic inches, developing 700 horsepower at 2,050 RPM. The engine proved its reliability on the 1933 flight orchestrated by pilot, politician, and bon vivant Italo Balbo. The A24R powered the flight of 24 Sia Marchetti SM-55 flying boats from Rome to Chicago and return. The Fiat A30RA design of 1930 was a smaller V12, making 550 horsepower at 2750 RPM from a displacement of 1,464 cubic inches. This engine was a direct development of the Fiat AS5 race engine, and it powered the 1934 Fiat CR32 fighter to a speed of 224 miles per hour. Diversifying into higher power air-cooled radial engines, Fiat built the A74, a 14-cylinder twin-row supercharged engine closely following the concept of Pratt & Whitney's R1830 Twin Wasp series. This engine was used in Fiat's CR42 advanced biplane design to supersede the Fiat CR32 and in Machi's MC200 Seita. Machi's chief designer Mario Castoldi was tasked to produce a modern monoplane fighter for the Regio Aeronautica in 1935. The MC200 Seita was the resulting design and was powered by the Fiat A74. The MC200 was the basis for a longer line of Machi fighters, which ultimately ended with their superior MC205 Veltro. While the American and Italian teams had previously dominated the Schneider competitions up through 1926, British engineering teams were not idle. Supermarine Aviation Limited's Reginald Mitchell designed a series of monoplane racers, starting with the S4 entered in the 1924 race. Damaged before the race and unable to compete, Mitchell nonetheless applied the lessons learned to the follow-on S5 racer for the 1927 event in Venice. Powered by the Napier Lion 7A direct drive and 7B geared engines, the Supermarine racers won first and second place in 1927 at a speed of 281 miles per hour. Rolls-Royce had been in cooperation with Supermarine to replace the Napier Lion engine with a new V12 design for their new S6 racer since 1928. Purpose-built for short-duration, high-power runs, the engine boasted a massive supercharged 37-liter displacement, 6-inch bore, 6.6-inch stroke, and a 6-to-1 compression ratio. At 1,900 horsepower, There were also a host of experimental features that were to pay dividends in future designs. The crankcase, cylinder blocks, and reduction gear housing were all cast from a special Rolls-Royce patented high-temperature aluminum alloy, and sodium-filled valves were introduced. The Supermarine S6 won the 1929 race, piloted by Flying Officer Waghorn of the RAF High Speed Flight at a speed of 328 miles per hour. For the 1931 competition, owing to worldwide economic crisis, the British government ceased funding for the race. Supermarine aviation was fortuitously funded £100,000 by longtime philanthropist in aviation developments, Lady Lucy Houston, keeping the entry alive. Supermarine built 2 additional S6B racers with an uprated 2300 horsepower Type R engine and won the 1931 Calshot event uncontested. Shortly after the race, Flight Lieutenant Stanforth of the RAF High Speed Flight attained a new world record at 407 miles per hour. In the year before Charles Lindbergh's transatlantic flight that put American radial engines squarely in the lead of aero engine technology, Pratt & Whitney set out to up the stakes on their WASP success with an enlarged radial, the R-1690 Hornet. The Hornet featured a displacement of 1,690 cubic inches, initially delivering 525 horsepower. The Hornet was selected for a venture intended to revive the failing Granville Brothers business. The GBR-6 was designed as a larger, longer-ranging touring sportster. It was selected by Floyd Odlum as an entry in the coveted 1934 McRobertson London to Melbourne air race to be flown by Jacqueline Cochran. A malfunctioning flap and resulting stabilizer damage forced Cochran out of the race at Bucharest, Romania. A string of additional unsuccessful race attempts ended with Francisco Sarabia Tinoco's flight from Mexico City to New York in 10 hours 47 minutes in May 1939. The Hornet was also the engine of choice for Boeing's revolutionary Model 299 in 1934. The 750 horsepower Hornet was superseded in that design by the competing Wright R-1820, a similar concept single-row large displacement radial. Pratt & Whitney further pursued the Hornet with a yet larger displacement R-1860 Hornet B, but in the fast-paced development period, each was outperformed by their two-row successor, the R-1830 Twin Wasp. The influence of Curtiss D-12 engine was apparent in Rolls-Royce designer Arthur Rowledge's 1926 Kestrel V-12 project. Incorporating the idea of cast aluminum cylinder blocks and eventually a centrifugal supercharger for improved mixture distribution, the 1,296 cubic inch Kestrel 1 first flew in 1927, rated at 450 horsepower. An improved 1B version followed with compression ratio increased from 6:1 to 7:1. The 525 horsepower Kestrel 1B further benefited from various other emerging technologies, including the use of higher octane fuels, affording the engine to be operated at higher supercharged boost levels, and pressurized coolant systems allowing more compact radiators. Hawker Aircraft Limited capitalized on the Kestrel engine's advantages with their new family of biplane fighter and light bomber designs, the Hawker Fury and Hawker Hart. The Fury was an agile single-seat fighter which bridged the older biplane technology with the emerging structures and power plants to come. Evident is the streamlined incorporation of the V-12 into its tight aluminum-skinned cowling. A bomber version of the airframe was concurrently developed in a two-seat arrangement, the Hawker Hart. The various versions were the Hawker Hind and the later Hawker Demon fighter. The Hart, Hind, and Demon were successfully marketed to many international customers, becoming a solid success for Hawker and Rolls-Royce alike. Developments at Pratt & Whitney followed a logical path from the successes of their previous designs. From their widely used and highly successful Wasp Jr., the two-row R-1535 Twin Wasp Jr. evolved. Originally rated at 650 horsepower, the twin rows of 7 cylinders were the same as those used in the R-985 Wasp Jr. This afforded designer Richard Palmer with an opportunity to employ a smaller diameter, more powerful radial engine into a very compact racing airplane to be built by the Hughes Aircraft Company. Advanced research at Caltech's wind tunnel facility helped the team of Palmer and Oedekerk conceive what is arguably the cleanest and most elegant airframe ever produced. Hand-built to exacting standards, utilizing machined flush riveting, and incorporating a retractable landing gear, the Hughes Racer emerged in 1935, ready to break existing records handily. On September 13, 1935, with its Pratt & Whitney R-1535 specially prepared to deliver up to 1,000 horsepower, Hughes performed a series of officially sanctioned passes near Santa Ana, California, at a speed of 352 miles per hour to set a new landplane world speed record. The H-1 was also configured with a set of longer span wings for transcontinental records. Hughes piloted the H-1B on January 19, 1937, non-stop from Los Angeles to New York in 7 hours, 28 minutes, besting his own previous record. Wright Aeronautical Corporation's journey in producing radial aero engines more or less paralleled that of Pratt & Whitney following the success of the Whirlwind series. The U.S. Navy had determined that their needs were best met with lightweight air-cooled radial engines rather than their counterpart V-12s, and thus helped establish Wright as a supplier of these engines. As originally built, the large displacement single-row Cyclone developed 525 horsepower at 1900 RPM in 1932. Wright incorporated cast aluminum crankcases and multiple cylinder cooling fin design advances, along with increased supercharger gear ratios to increase power output over new versions to 895 horsepower. Grumman's first Navy fighter, the FF-1, evolved through its F-2F and F-3F series to take advantage of the newest 950 horsepower Wright Cyclone engines in the F-3F-2. Concurrent with further development, including a switch to forged steel crankcases and more refined cylinder cooling fins, Wright continued to increase power output, which revealed the problems of torsional vibration in the crankshaft. Wright's Roland Chilton designed a pendulum system to swing a counterbalance out of phase with crank vibrations to nullify them. The Cyclone was licensed for production in the Soviet Union in a version converted to metric standards by Shchetsov as the M25. During the mid-1930s, Soviet designer Nikolai Polikarpov utilized the Shchetsov ASH-62 follow-on to the license-built Cyclone for his I-153, I-16, and I-15 fighter designs. The I-16 was the world's first production cantilever low-wing monoplane fighter with a retractable undercarriage in frontline service. The Polikarpov fighters were seen in combat in China against the nimble Japanese Nakajima and Mitsubishi fighters, and in Spain against the Messerschmitt 109s during the 1936 Civil War. Douglas Aircraft launched their revolutionary DC series of commercial transports in mid-1933, powered by the 695 horsepower Wright Cyclone. Within a year, their enlarged DC-2 flew with Cyclones and finished second in the 1934 McRobertson Trophy race entered by KLM Dutch Airlines. Douglas' crowning achievement in the period, their unequaled DC-3, followed and was built to use either the Wright Cyclone or the Pratt & Whitney R1830 Twin Wasp. Capitalizing on that success, Douglas competed against Boeing for the 1934 U.S. Army heavy bomber contract. Owing to the crash of Boeing's Model 299 and some political maneuvering, Douglas won the initial contract in 1936. The B-18 was a DC-2 modified with a deeper fuselage, longer wings, and military hardware. Boeing's B-17 rose from the ashes of the crashed Model 299 to literally define the term heavy bomber for the rest of the 1930s. 4 turbo-supercharged Wright Cyclones powering the heavily armed Flying Fortress soon regained the contracts with the Army in light of deteriorating political climate worldwide. Lockheed's advanced series of Lodestar airliners followed suit with Cyclone power. In the period of the mid-1930s, the U.S. Navy kept pace with modernization of their fighters, first with the Brewster F-2A Buffalo, their first monoplane fighter. The Douglas SBD Dauntless Scout Dive Bomber series, and the consolidated PBY Catalina Long-Range Reconnaissance Patrol Bomber. During World War II, the Navy sought a second producer for many of its fine Grumman fighters and bombers, selecting the General Motors Eastern Aircraft Division. The FM-2 was produced to significantly enhance the Wildcat's performance with all of the Cyclone's latest improvements. With the 1,350 horsepower Wright R1820-56, the Wildcat's low-level performance significantly improved the lifespan and effectiveness of the series. Today, our journey through the 1920s and 1930s has demonstrated how aeronautics and power plant technology took flight following the First World War. From wire-braced wooden structures powered by less than 300 horsepower to modern internally braced aluminum airframes powered by many thousands of horsepower, a new generation of technologies still beckoned to push the boundaries of possibility yet further, faster, and higher. In Part 2, we will take a look at the succeeding decade, including the extreme developmental period during the Second World War.